how do you actually build a machine that can think? It's a question that has completely captivated mathematicians, engineers, and philosophers for decades. I mean, we interact with artificial intelligence every single day, right? But how often do we actually stop and ask, how are these incredible systems actually made?
Well, welcome to This Explainer. Today, we are stripping away all the sci-fi hype to look directly under the hood of artificial intelligence. We're going to trace the fascinating evolutionary journey of the making of AI, and we'll explore exactly how we went from basic, clunky calculators to the incredibly complex, evolving minds that are reshaping our entire world today. So, here is our roadmap for today. We'll kick things off with Section 1, the dream of AI, and then move right into the shift to machine learning. From there, we'll unpack deep learning and neural nets, define the big difference between narrow versus general AI, and finally, look at building the AI future.
Okay, let's dive right into this. Part 1, the dream of AI and simulating intelligence.
You see, the original scientific goal wasn't just to make a faster calculator. Actually, scratch that. It was about simulating human intelligence inside a machine, giving it the genuine ability to learn and reason. To really understand the making of AI, we've got to look back at how those early theoretical blueprints became reality. Back in the 1950s, computers were basically just large-scale math machines. But in 1950, British mathematician Alan Turing envisioned a machine that could expand way beyond its original programming, proposing the famous Turing test to see if a machine could actually imitate human thinking. Then, in 1956, the field of AI was officially founded at the Dartmouth Conference. Those early theories sparked decades of intense research. Fast forward to the year 2000, and MIT launched Kismet, a literal, physical, social robot capable of identifying and simulating human emotions using just sensors and a microphone. We went from pure theory to machines that could actually mimic feelings.
And this quote right here brilliantly illustrates the mindset of those early pioneers. At that 1956 Dartmouth conference, a small group of researchers stated, "Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." So early engineers honestly believed they could explicitly map out and hardcode every single rule of human intelligence. This was the early knowledge base approach. They literally tried to write out endless lists of logical inference rules for the computer to follow. But well, that brings us to part 2. The shift to machine learning and learning from data. Because that early knowledge base approach, it eventually hit a massive brick wall. Human engineers simply couldn't formally write out all the tacit, intuitive knowledge required for complex tasks. It's just too much. So the absolutely crucial turning point in AI history is this major pivot right here. We had to move away from explicit programming, where we give a computer rigid, handcrafted rules and logical decision trees, and shift toward machine learning. Machine learning, or ML, seeks to automatically learn patterns from data examples without strict, hard-coded rules. It essentially relieves humans from the impossible burden of trying to formalize everything we intuitively know. Let me use an analogy here to make this incredibly clear. Think about teaching a child what a sports car is. You don't sit them down and recite a strict, explicit list of rules about engine size, chassis height, and aerodynamics, right? No way. You show them examples. You point at a sports car on the street and say, hey, that's a sports car. You show them a normal sedan and say, that is not. Over time, their brain naturally learns to recognize the pattern. And this is exactly how machine learning fundamentally works. We feed the computer data, and it learns entirely by example. Which perfectly sets up part 3, deep learning and neural nets, where we start modeling the brain. As data availability and computing power completely exploded, engineers realized they needed to scale up this learning by example method. And to do that, they looked for inspiration from the most powerful computer in existence, the human brain. This led to the development of the artificial neural network. Basically, it's a collection of artificial neurons, or nodes, trained to recognize patterns, loosely modeling the biological neurons in your own head. Once this network is trained on a massive amount of data, it can recognize those exact same patterns in entirely fresh, unseen data. Now, what's really fascinating here is the architecture. Let's break down how a deep neural network actually works into 3 simple logical steps. Step 1. Input data. You feed information into the system, say thousands and thousands of pictures of cats. Step 2 is the hidden layers. The data passes through at least one, but usually multiple hidden layers of nodes. Each node applies a mathematical function and a weight. And if the result crosses a specific threshold, boom, it transmits the signal to the next layer, just like neurons firing in your brain. Finally, step 3, output prediction.
The network makes a decision, recognizing the pattern and outputting an answer. When a network has at least two of these hidden layers, we call it deep learning, and that is the exact technology driving today's massive AI boom. All right, moving right along to part 4, narrow versus general AI, specialized versus human.
It is incredibly important to clearly define what we have successfully built so far versus the ultimate holy grail that engineers are currently chasing. Today, virtually every single AI you interact with falls under the category of narrow AI. These are systems designed to perform specific, limited tasks. Whether it's the AI mastering complex strategy games like chess, the algorithm powering your web search engine, or the virtual assistant on your phone, they are highly, highly specialized. Even modern generative AI, despite how incredibly impressive it seems to us, is still technically narrow because it's focused on specific domains. Contrast that with general AI or AGI. This is the next absolute frontier. AGI aims to replicate human-level intelligence, reasoning, and cognitive skills across all types of problems. An AGI system could seamlessly shift from computer vision and language translation to understanding complex social situations and actually being sensitive to emotions, completing virtually any cognitive task, at least as well as a human could. This is what all the major research labs are striving toward today. So let's look at part 5, building the AI future with next-gen AI systems. How are engineers actually trying to bridge this gap from narrow systems to general AI? Well, we're seeing a massive shift right now in how AI is made. First, we have generative AI. This marks a massive shift from rule-based automation to intelligent, self-evolving systems. These systems can actually learn new tasks autonomously and even generate their own training data through simulation. Next, there is agentic AI. This is a really cool hybrid approach that combines analytical AI for structured decision-making with generative AI for adaptability. The goal here is to make modern robotics and software capable of working completely independently in messy, complex, real-world environments. And finally, we have a critical piece of the puzzle, explainable AI, or XAI. As this quote from IBM highlights, XAI implements specific techniques and methods to ensure that each decision made during the ML process can be traced and explained. Now, why does this matter so much? Because as we build AI that evolves on its own, generating its own data, and making completely autonomous decisions in the real world, we desperately need to be able to trace its logic. If we don't, these systems risk becoming a giant, uncontrollable black box, where even the creators themselves don't understand how the machine arrived at its answer. Which leaves us with this final, pretty profound question. As AI learns to build and evolve itself, will we still understand how it thinks? We've journeyed from scientists trying to hand-code every single rule of human logic to neural networks that learn by example, all the way to self-evolving autonomous systems.